No, sir.
Okay, not, sorry, yeah.
No questions, sir.
So in that case, let me make some comments. Yeah, I really want to finish this today, if possible. Okay, in MCAS unit, the energy eigenvalues are given by minus R divided by N squared, where R is a constant called the Rydberg constant. And the Rydberg constant is the ionization energy of the ground state of the hydrogen atom. And is given by, R is given by half m E squared divided by 4 pi epsilon naught H bar whole squared. And in electron volt, it's 13.6056923 electron volt. So that's comment number one. Number two is that the energy levels for the full quantum treatment of the hydrogen atom that we see here gives the same energy levels as the Bohr atom, which is remarkable because Bohr did not know. When Bohr derived his atom, there was no one knew about Schrödinger equation or anything like that. They just had a bunch of rule of thumb, and Bohr just used those rule of thumb. Okay, number three is for a given n, L is less than n. And this leads to the following degeneracy pattern of the energy levels. So the degeneracy pattern you get is something like this. So I'm going to draw a picture. So on the y-axis is the energy. On the x-axis is angular momentum. And here I'm going to, okay. So this is, okay. So this is the n equals to infinity level, right? So the energy at, what is the energy at this level?
Zero.
Yeah, exactly. If you give it more energy, the electron and the hydrogen atom, they become a different quantum system where there are two free particles. They are no longer bound in the atom. Okay, then they're ionized. So then it's a different problem. It's a problem between, interaction between two free particles who are interacting whose total energy is positive and who are interacting through a Coulomb potential. Okay, that's a different problem. So above this, always remember the states are continuous. Energy is not continuous above, is not quantized. Okay. In quantum mechanics, energy is only quantized for negative values of total energy. Okay. So this direction is where minus of E goes. And this is n equals to 1. So I'm going to, okay, for n equals to 1, we have only one value of L, right? L is 0. For L0, what is the degeneracy of the angular momentum states? How many states do we have? For L0, how many states do we have?
1.
Right.
Yeah.
Because it's 2L plus 1, right? So we have that. But L cannot be more than 0 because it has to be always less than n. So then we get to n, the value of n being, let me use a different color. This is n equals to 2. And again, the first one is L0, so here we have 1, right? But in this case, when n is 2, L can also be 1. So this is, we draw here the L equals to 1 state. So L equals to 1. So how many state can we associate with this guy, with this n energy level? How many angular momentum degeneracy?
3.
And then n can go to, n becomes 3. Okay, so, and the distance between them is decreasing because 1 over n squared, right? It's like a parabolic, like the distance is decreasing the way, yeah. So let's, I'm just being heuristic here. Okay, let me just do it here. Let this be n equals to 3. The first one is, of course, 1. And this guy is, of course, 3. But then we have another possibility here where L is equals to 2. So what is the degeneracy in terms of angular momentum?
Uh, 3.
Well, we already have 3, right? For what is L is 2, so what is the degeneracy when L is 2?
Let me see.
5.
5. All right, cool. And then we have, we go from there to n equals to 4. N equals to 4 is somewhere here. So what is the, so this is, of course, 1. This is 3. This is 5. What is this thing?
Seven.
Right. Okay, so let me just do something. Let me take this whole picture and move it so that I can make some room. Okay, good. And now, total degeneracy for a given n, total degeneracy for a given n. For this is 1, right? For this guy, this is 4. For this guy, this is 9. For this guy, this is 16. Okay. So we can then generalize the total number, of degenerate states for a given n is 1 plus 3 plus 5 plus ... 2n minus 1, right? And that's going to be equal to n squared, okay? 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, okay? Okay, any questions?
No, sir.
All right. Okay, so next comment. These comments are very important. You should try to remember them, okay? And understand them, of course. So for a given n, we have two kinds. We have two kinds of degeneracies. One is, different L's, states with different L's. States with different L's. So here, this is L1, this is L0, this is L1, this is L2, but they have the same energy. So this kind of degeneracy is known as accidental degeneracy. And why is that? Because this degeneracy does not arise from some symmetry. From some symmetry. That is, there does not exist an operator O such that it commutes some symmetry operator such that it commutes with the Hamiltonian, right? So if we give an R dependent perturbation to the system, what does it mean? Means that suppose that the system comes in contact with another system such that the total Hamiltonian is the Hamiltonian that we've been studying, hydrogen, and something which is some function just of R, where lambda is a small parameter. So this is what it means to give a perturbation. Then what will happen is that all these systems, this degeneracy will be lifted, meaning that the different values of L would then we would have different energies, okay? The second is that the degeneracy due to spherical symmetry. Okay. And that degeneracy is not lifted by a perturbation like this, because a perturbation like this is going to respect spherical symmetry, right? So that degeneracy would be lifted if the perturbation were to break spherical symmetry. Okay, any questions?
No, sir.
I want you to understand the term accidental symmetry, okay? That is accidental degeneracy. That is degeneracy not due to asymmetry. And in the real world, you know, the hydrogen atom will always be interacting with something, right? And therefore, you know, a lot of those degeneracies would be lifted. So comment number 4. Comment number 5 is that, you know, historically, that is before the analysis of hydrogen atom, you know, experimentalists observed the spectrum. I told you what the spectrum is, right? How to derive the spectrum. The spectrum, and historically the spectrum, the frequency was given by the Rydberg constant divided by h, Planck's constant, by 1 by n prime squared by 1 over n squared. So these were series which were given by different names for different values of n prime. If n prime was 1, then that series of frequencies was called the Lyman series. And then for n prime equals to 2, it was called Balmer series. For n prime equals to 3, it's called the Paschen series. N prime equals to 4, it's the Brackett series. So as you can see, you know, this is very easy to derive from our energy eigenvalue equation, because all that this is saying is that this is the difference in the energy levels. So if I go back to my energy, each of this series is essentially, the first series is all the transitions from all the other states to this ground state, right? So this is the first series, you know, and of course there's other. And the second series is just all the states, relaxing to the first excited state. And similarly for the others. Okay, so this is the Lyman series, this is the Balmer series, this is the Paschen series, this is the Brackett series. So we see how beautifully quantum mechanics explains the experimental phenomena of spectroscopy. Okay, and if you're interested in, say, astrophysics, this is the window to the universe, because, you know, when we look at stars from distant the light from distant stars and galaxies, how do we know what they are made out of, right? What we do is that we take the light and we run it through a prism, you know, through a spectrometer, and then we look at, you know, what are the frequencies that are present. And if you see the pattern, the pattern of hydrogen atom that we are familiar with, we know that you know, the light that is being emitted from that distant, you know, star or galaxy has hydrogen in it. And, you know, different elements will have different signatures, because their energy levels would be different. And we can chart those things, make charts of those in our lab down here on Earth, which is something we did as an undergraduate. And then when we look into the stars, we say, look, we have exactly the same pattern in this starlight, and therefore that that star must contain the same chemical. Okay? So this is an amazing, beautiful application of quantum mechanics.